User requirements define what a system must do and the constraints under which it operates. They are the foundation that guides design, development, and testing. Requirements are of two kinds. Functional requirements describe features the system must provide. Non-functional requirements set quality targets, for example, response time, security standards, and availability. User requirements are written simply so anyone can understand them. They describe what users want. For example, the ability to register, search items, and pay securely. System requirements translate user needs into precise technical terms for developers and testers, such as encryption methods, performance limits, and interface behaviors. Remember the differences. User requirements express user expectations in plain language. System requirements are the technical translation. Functional tells what the system does. Non-functional tells how well it should perform. Clear requirements align stakeholders and the development team, guide design and testing, help estimate cost and timelines, and reduce the risk of rework or project failure. In short, user requirements capture what users want. System requirements define how to build it. Functional requirements specify actions. Non-functional requirements define quality. Good requirements equals success.
Specification, or SRS, is a document that defines what a software system should do and under what conditions it must operate. It serves as a contract between stakeholders and developers, ensuring clarity and avoiding confusion before development begins. An SRS defines both functional requirements, what the system must do, and non-functional requirements, how it should perform. Its purpose is to reduce misunderstandings, serve as a reliable reference for design, coding, and testing, and act as a baseline for scope, cost, and schedule estimation. The structure of an SRS document is divided into 4 key sections. The introduction covers purpose, scope, and references. The overall description includes the product perspective, types of users, and environment. Specific requirements detail both functional and non-functional needs, along with interface requirements. Finally, appendices provide supporting details such as diagrams, glossaries, and additional data. A good SRS should be complete, covering all requirements without gaps. It must be clear and unambiguous so there's no confusion. It should be consistent, free from contradictions. Every requirement should be verifiable through testing. The document must also be modifiable to adapt to changes and traceable, so each requirement can be tracked from origin to implementation. There are many approaches to writing an SRS. The IEEE 830 standard is the most structured and widely used. Use case-based SREs describes user interactions. A prototyping approach refines requirements while stakeholders test early versions. Other approaches include agile user stories, where requirements are written as short scenarios. Tabular formats use requirement ID and priority for traceability. A hybrid approach combines multiple methods for flexibility. Let's look at an example, SRS for a library management system, written using the IEEE 830 format. In the introduction, the purpose is to automate library tasks like managing books and members. The overall description covers book catalog functions, types of users like librarians and members, and the system environment, such as Windows and a MySQL database. Next are the specific requirements. Functional ones include adding books, registering members, issuing and returning books, and calculating fines. Non-functional ones specify that transactions should finish within 2 seconds, that only authorized librarians can modify records, and that the system must be reliable and easy to use. The interface requirements describe the user interface, database integration, and LAN communication. Finally, the appendices include supporting materials like a glossary, sample forms, and system diagrams. This example shows how an SRS covers both what the system does and how well it should perform.
Requirement elicitation is the process of gathering and understanding stakeholder needs.
As the first step in requirement engineering, its quality directly impacts the success of the project. The objectives are to understand what stakeholders really need, resolve conflicting demands, define the project scope, and capture clear agreed-upon requirements. Elicitation follows key steps: identify stakeholders, choose the right techniques, gather information, document it systematically, and validate with stakeholders for accuracy. Common techniques include interviews, surveys, observation, and workshops. Other approaches are document analysis, prototyping, and use cases, each chosen based on the project's needs. Elicitation often faces challenges such as incomplete or unclear requirements, conflicts among stakeholders, hidden needs, and frequent changes during the project. Requirement validation ensures that the captured requirements are correct, complete, and accepted by stakeholders before moving forward. In summary, elicitation gathers stakeholder needs, applies suitable techniques, validates them early, and builds the foundation for successful software projects. Welcome. In this video, we'll explore requirement modeling, different ways to represent and analyze software requirements before development begins. Requirement modeling is the process of creating structured or visual representations of requirements. It bridges user needs and system design, reduces misunderstandings, and ensures clarity. We use requirement models to simplify complex requirements, validate them with users, spot conflicts, and give developers a clear roadmap. There are many ways to model requirements. In this video, we'll focus on 5: decision tables, event tables, state transition tables, Petri nets, and CRC models. Decision tables are a structured way to represent conditions and the actions that follow. Each column in the table represents one possible rule or scenario. They are especially useful when business logic is complex, like loan approvals or insurance claims, because they ensure no condition is missed and all cases are considered. Event tables capture all the important events that affect the system. Each event has an input, the process it triggers, and the expected output. This makes them especially useful in real-time or interactive systems. For example, in an online shopping cart, the event add item triggers a process to update the cart, and the output is the new cart total displayed to the user. State transition tables describe how a system moves from one state to another, depending on the input. Each row maps a state, an input, and the resulting next state. This is especially useful for event-driven systems. For example, an ATM moves from idle to processing when you insert a card, then to dispensing cash after entering a valid PIN. Petri nets are both graphical and mathematical models. They use circles called places, rectangles called transitions, and tokens to show system behavior. Petri nets are powerful for modeling concurrency and synchronization. For example, in a ticket booking system with multiple users, Petri nets can model how seats are reserved and locked to avoid double booking. The CRC model stands for class, responsibility, and collaborator. It helps identify key classes in object-oriented design, what each class is responsible for, and how classes collaborate. For example, in a library system, the book class stores book details. Here's a quick glance at 4 requirement modeling techniques together: event tables, state transition diagrams, Petri nets, and CRC models. Each give us unique insights. Together, they ensure requirements are clear, structured, and validated from multiple perspectives. Requirement modeling improves understanding, reduces ambiguity, and helps detect errors early, saving both cost and time. It also acts as a blueprint for design and coding while validating requirements with stakeholders. Industries like banking, healthcare, and e-commerce rely heavily on these techniques. Solve the problem of scheduling academic meetings by providing a simple and organized digital platform. This system features include student and teacher registration, secure login, and appointment booking with flexible time slots. Teachers can approve or reject requests, while students receive timely notifications and reminders. An admin panel ensures smooth monitoring of all activities. Functional requirements of the system are: students can create profiles, view teacher availability, and request appointments. Teachers manage their schedules and respond to requests. Admins have control over user management and can access system reports for transparency. Non-functional requirements of the system are: the system provides real-time updates within seconds, ensures security through encryption and authentication, and offers a user-friendly design accessible on any device. It also guarantees reliability with high uptime and backup. This is the case diagram of system that explains the workflow of the system. The benefits of the system is: this booking system saves valuable time for both students and teachers, improves transparency and communication,